So recall that we have what we call a Pythagorean identity by understanding that cosine and sine are the lengths of the two legs of a right triangle. So this is cosine here, this is sine, because this point has coordinates cos sine. And on their unit circle, their hypotenuse is 1. So cos square of theta plus sine, oh, and I don't want to write it like that. So cos of theta squared plus sine of theta squared equals 1. But I've mentioned, right, that we can actually write it like this by taking out the brackets and putting the power of 2 in between the function's name and the argument. You get a different way of writing down the equation, and this is a notation that's valid for trig functions. Okay. All right. So for example, if I had log of x squared, I would not put the 2 in between log and x. Okay, that's not something that's a notation that's allowed. So we would always put brackets and put the square above it. The reason is that it's pretty rare that we square logs, or if we do, it's not all the time, but cosines and sine, we square them all the time. So this is why they've introduced this notation that accelerates the way we can write them. So this is equation Pythagorean identity number 1. It's the main one. After that, you can get a second one by taking this identity. Okay, actually I'm going to write it like that so that you can see better what's going on. And we're going to divide throughout on both sides by cosine of theta squared. So I divide everywhere by cosine of theta squared. So I'm allowed to do that. Like once you have an inequality, you're allowed to perform the same operation on both sides. So here I divide by cos square of theta. Now the first term is cos square of theta over cos square of theta, so that's 1. This second term, actually I'm going to regroup everything as a single fraction squared. This is sine squared over cos of theta, all that squared. And this one is 1 over cosine, all of it squared. Why did I do that? It's because what you see in the bracket here is tangent. So tangent is squared. So I'm going to use the same notation that I have for cosine. If tangent is squared, I'm going to put the 2 in between the name for tangent, the name of the function, and the argument of the function, which is theta. Cosecant, 1 over cosecant, sorry, is secant. Also, that is squared, and that gives us our second Pythagorean identity. So there's a relationship between the tangent of an angle and its secant, and it's obtained through this relationship. 1 plus tan squared is secant squared. Now there's a third one. I start again with my main Pythagorean identity. For the previous identity, I divided throughout by cos squared. Now I'm going to divide throughout by sine squared. Okay, and regroup this together as something squared. Sine over sine, that's 1. 1 over, and this is 1 over sine squared. Now cosine over sine, this is cotangent. So what do we have here is cotangent squared plus 1 equals 1 over sine, this is cosecant. So there's also a relationship between cotangent and cosecant. And this is our third Pythagorean identity. So just to show you an example of that, those identities in action. Let's say I calculate the tangent of pi over 3. Okay. And then after that, I'm going to calculate the secant of pi over 3 and show that they are related through this identity here, that it works. So tangent of pi over 3, what is that? This is sine over cosine. Okay, sine of pi over 3, what is that? So I draw, so of course I draw it on the side here. Eventually you do this in your head when you get good at it. So you see this triangle here. So the sine is the height here of this triangle, and it's the largest side, so that's root 3 over 2. Cosine is the smallest side, that's 1/2. As you simplify, you get root 3. Let's look at secant now, because we know that they should be related to one another. So this is 1 over cosine. Now cosine we said is 1/2, so 1 over 1/2 is 2. Now, so let's verify the identity. Let's verify that tan squared, I'm going to write it as it was written initially. So 1 plus tan squared is secant squared. I was going to write tan squared plus 1 is secant squared, which is obviously the same thing. Okay, so I'm going to look at 1 plus tan squared of the angle pi over 3. So I'm looking at this identity for a specific case and see if my example validates the identity that should be true in general. So 1 plus tan squared of pi over 3, that's 1 plus root 3 squared. And this is 1 plus 3, this is 4. Let's see if we get 4 by, I'm going to look at this side, sec squared of theta should be equal to 4. Sec squared of my theta, which is pi over 3, that's 2 squared, and 2 squared is 4. So you can see they're both equal, right? So equal. Okay, so we can truly see that when theta is pi over 3, the identity is valid. But what I've done before is showing that it's valid all the time. This is just checking on a specific example that it actually works.